This is an extra video, and we're going to be covering the Laplace equation on a sphere. So it's not going to be a topic that's going to be asked about in the final exam. It's just a non-trivial example of what can be done when you have the Laplace equation on a non-trivial domain. So the first thing we do is we move to spherical coordinates. As we have done when we were dealing with a disk, we were doing the same thing. We're going into coordinates that are a bit nicer to work with. So we're introducing three new coordinates. We are in 3D space, so we still need three coordinates to define one point. And for any point inside a sphere of radius r, we define rho as the distance of the point we're looking at with respect to the origin, theta as the angle between the y-axis and the projection of the point on the xy plane, and psi, that is the angle between the segment connecting our point to the origin and the z-axis. So we now have three new coordinates. Rho, that goes from 0 to infinity if you're taking the whole R3 plane. Psi, that goes from 0 to 2 pi. And theta, that goes from 0 to 2 pi. It's the same to go from 0 to 2 pi or from minus pi to pi for theta. And we have this transformation. X, y, and z can be written in the new coordinates as rho sin psi cos theta for x. Y is rho sin theta sin psi. And z is rho cos theta. While rho itself is just the Euclidean norm in the xy coordinates, so it's x squared plus y squared plus z squared, all of that square rooted. We do a change of coordinates of the Laplacian. This time I'm not going to go through the steps to go here at all. I'm just going to claim that we can rewrite the Laplacian that in the xyz coordinates is just delta squared over delta x squared plus delta squared over delta y squared plus delta squared over delta z squared as this blob that I'll call L. So I just want you to look at the structure this thing has. You don't have to learn this by heart. There are plenty of books that can give you these formulas and explain how you get there. But I'd like you to concentrate on the format that this thing has. So there is 1 over rho squared at the beginning. And then you have 3 blocks. The first block only has derivatives with respect to rho and multiplication with respect to rho squared. The second block has sin psi popping up and derivative with respect to sin psi. The last block is a bit mixed because it has derivatives with respect to theta and sine with respect to psi. If you notice, it's still a linear operator. All the pieces you have are all linear pieces. So we can write this operator as L and just say that applied to U is LU. So we're going to consider the Laplace equation on the sphere of radius C as LU equal to 0, and we want some boundary condition at the boundary of the sphere. So for rho equal to C, we have that U, that now is U computed at rho equal to C, psi and theta, and we are setting this as a function of psi. So theta, that is where you are in the projection in the xy plane, doesn't matter. And psi goes from 0 to 2 pi. We say that if u, depending on rho psi theta, actually does not depend on theta, so it can be written as a function of rho and psi, then we call u axis symmetric. This is the idea that you can anything that happens on the sphere happens everywhere in a ring. If u is axis symmetric, then the derivative with respect to theta in our linear operator just disappears. And it simplifies even further. We can write it as this new equation. So we're claiming that the solution to our Laplace equation with boundary conditions that do not depend on theta at all is an axisymmetric solution. So it's a solution that does not depend on theta. And that works well because when it doesn't depend on theta, the mixed term at the end disappears. So the term that had both psi and theta is not there anymore. And we can write it even more simply as this formula. So it's u rho rho, so second derivative with respect to rho of u, plus 2 over rho u rho, plus 1 over rho squared u psi psi, so second derivative with respect to psi of u, and cotangent of psi divided by rho squared times u psi. And we are setting all of this equal to 0. We claim that in this situation, we can use again separation of variables. So we're going to split u as a function of rho and psi in two functions, r being a function of rho and capital psi being a function of psi. If we apply this and we chunk it through our simplified L operator, we retrieve, and we do as before, we try to divide all the things that depend on rho and all the things that depend on psi. Then we go through the steps. We retrieve that rho squared times r second plus 2 rho r prime divided by r is equal to minus capital psi second plus cotangent of little psi times psi prime divided by psi. As we have done multiple times when we do with separation of variables, we notice that one block depends all on r, the other depends on psi. Therefore, when we change r and psi, these two blocks need to stay constant. So we say that it's equal to a constant, and we give this constant the name k squared. As we did before, we're claiming that k squared, if you're taking it complex, dispense any real number. Hopefully, we're chosen it in such a way that we're going to notice that k can be actually real and not complex. But now we can split the two problems into solving rho squared r second plus 2 rho r prime minus k squared r equal to 0, and psi second plus cotangent psi times psi prime plus k squared psi equal to 0. We want to find the change of variables on top of the change of variables that we already did, such that one of the two turns into a Sturm-Liouville problem. We're actually going to concentrate on the second one, and we want to find a change of variables such that it is a Sturm-Liouville problem. What do we need? Well, we have part of the usual structure of the Sturm-Liouville problem. We have psi multiplied by k squared. K squared is our eigenvalue. And then we have psi second plus something times psi prime. So the structure is roughly there. What we do need is breaking this cotangent of psi in such a way that we have the p of psi times and then p prime of psi in the right positions. The change of variables that is needed is transforming cos psi into mu. Now mu goes from -1 to 1, and we can rewrite the rule function. Needs to be a bit careful, but k squared psi stays the same. And we're changing the derivative with respect to psi into derivative with respect to mu, and that gives different coefficients in front. So if we do this transformation of variables, we get to 1 minus mu squared times psi second derivative with respect to mu minus 2 mu psi derivative with respect to mu plus k squared psi equal to 0. Where now psi is a function of mu, not of psi anymore. And you can look at it and say, well, now it's a Sturm-Liouville problem, it has the right shape. And if you remember, this actually is the Legendre equation. So we have specifically solved this type of Sturm-Liouville problem before. And we want to look at what are the boundary conditions. So first of all, we have that p, the coefficient in front of psi prime that is derived, needs to be 1 minus mu squared. P as plus and minus 1 is equal to 0 then. This is a singular Sturm-Liouville problem. This requires, if we want to solve it as a Sturm-Liouville problem, that the boundary conditions are that psi computed at plus or minus 1 needs to be bounded. This is also reasonable from a physical perspective. So we have something reasonable. If we remember what we have done in the Legendre equation, we remember that we have bounded solutions only for certain values of the eigenvalue of the Legendre equation. In particular, the values that we need is that k squared is equal to n times n plus 1 for n going from 0 onwards. So we have that psi as a function of mu is equal to any nth Legendre polynomial with respect to mu that is equal to, because of the change of variables we did, any Legendre polynomial computed at cos psi. We can do this, the Legendre equation is a Sturm-Liouville problem, so we have this double information, first coming from the Legendre equation part in which we solved it, and part about the Sturm-Liouville problem knowing that this the Legendre polynomials are a base for whatever set of functions that satisfy the boundary conditions. So now that we have fixed k, we want to solve R for R. So we have R rho, and we have this equation that is rho squared R second plus 2 rho R prime minus k squared n R equal to 0. Up to the fact that there is a minus there in front of the k squared, this could look like a Sturm-Liouville problem. But it's not how we want to look at it. We want to look at it as a Cauchy-Euler equation. So, in particular, because we don't have the right boundary conditions, so we cannot solve it as a Sturm-Liouville problem. So we want to solve it as a Cauchy-Euler equation instead. And from the Cauchy-Euler equation, we know that the solution has the form of Rn rho, so where n depends on the k squared n that we have introduced, is the sum of an rho n plus bn rho n plus 1 for n going from 0 to 1 and so forth. Now we can check the values that we want. So we can write u as an infinite sum of Rn times Pn computed at cos psi. We replace Rn, and we have this infinite sum of the Legendre polynomial computed at cos psi times a block that is an rho n plus bn rho n plus 1, divided rho n plus 1. We need to find a and b by imposing the boundary conditions. We need two boundary conditions. On one hand, we have that from the Laplace problem, when we compute u at c for rho equal to c, we have f psi. On the other hand, at rho equal to 0, we want something physical. So we want that u0 psi is bounded. This means that bn needs to be equal to 0, otherwise anything divided by rho at the power n plus 1 for any value of n when rho tends to 0 would explode. So bn is equal to 0 for all n. Then we need to determine an with the other boundary condition. But the other boundary condition we can use through the fact that we know that the Pn cos psi is a base for whatever. So using the information from the Sturm-Liouville problem, we can write an out.